Continuing with the design of the combined foundations, herein we are starting with the design problem. An exterior column of this size having a dead load and live load and an interior column of this size having a dead load and live load is given. These are 5 meter apart, center to center. Design a rectangular combined footing, not the dowels or supplies is carried to a depth of 1.5 meter where the gross allowable bearing capacity is 165 kilopascal. The outer edge of the exterior column is the property line and the outer edge of the exterior column. So that x1 is known. X1 will be very small value from the center of the column to the outer edge of the column. So that will be the half of the column size. It means that average density of the backfill material of footing and concrete is this one, while the filling from the ground floor to the plinth level is 0.75 meter and density is 1900, and design the footing FC prime and FY for this value. This data is given for the foundation design. You have all the data, P dead, P live, exterior, interior column. The live load reduction is 20%. The dimension x1 is all the time the distance from the known distance on the one side of the footing. So center of the column to the edge of the footing. So it is 0.15 meter. FC prime is given. Fy depth of the footing is 1.5 meter. Density of the soil is 2100 kg per cubic meter, and the density of surcharge and the depth of the surcharge, this is basically the fill above the soil level. From the ground level to the plinth level, there is another type of the fill which is 1900 dense. In this way, you first step is to get the load on the exterior column. The exterior column is the left-handed column, and the P2 is the interior column, is the right-handed column. You multiplied by the live load value with the live load total load kilonewton is multiplied with the 0.8 to reduce the live load. Now what is the allowable net bearing pressure? The total bearing pressure minus the overburden. Overburden of the soil is 1.5 into 0.5 into 20, 100. And the second overburden is the 0.75 meter thick into the 1900. Convert it into the kilonewton and allowable net bearing pressure is computed. Then the resultant is computed, total resultant force is computed. Now you apply the Varignon theorem and take the moment at the left-handed column center. You take the moment at the left-handed column center. That comes out to be the left-handed column moment is P2 into S, the load, the moment of the right side column, and the resultant moment is R into X bar. So X bar is equal to 2.992 meter. And as I told you that X bar plus X1 is equal to L by 2. So X1 is, I told you that your footing is just at the boundary of that column is at the boundary of the property line. So just the X1 is very small value. X1 is very small value. So this is the case actually which is this way that you are designing the foundation which is where the column is column is like this, just at the boundary. It's like that. It's like that case. This column width is 300 millimeter. This column width is 450, right hand column. So it means that your foundation is basically, you have to build the foundation, which is in the plan view. It is like in this way you have to. So x1 is from the center of the left-handed column to the edge of the column 0.15, and x bar is the location of the resultant. So resultant is basically comes out somewhere here, which is computed. X bar plus x1. So next one is the length of the footing, as the resultant is comes out to be x bar plus x1, location of the resultant. So it means that this resultant should pass through the L by 2. L by 2 is x dash plus x1. So 2 times that is the length value. So 2 times x bar plus x1, that should be the length of the footing. Say you can round it up. So the length is determined from the length, the width of the footing is determined. So area is determined in such a fashion that the resultant is passing through the centroid of the footing. The width is equal to the total load divided by the net allowable bearing capacity multiplied by the length. That gives you the width. You can increase that slightly. So the area provided is larger than the area required, because the area required is the total load divided by the net allowable bearing capacity. So footing design is not difficult, but it is a first point. Important thing is the geotechnical design, the area computations. And next important point is the computation, the right shear force and bending moment. But for that you need the computation of the bending moment and shear along the longer direction. So the load along the length of the footing per unit length. So along the length in the longitudinal direction, how much load is acting? So the load acting along the length is QU multiplied by the B value. So this will give you the load. I told you that the load acting along the length will be total pressure, factored pressure, multiplied by the B. So factored load is computed. First of all, 1.2 times dead load plus 1.6 times live load. Sum of that load divided by the area provided. That gives you the QU. And QU is 179.05. Multiplied by the width of the footing, it gives you the UDL. We have to design the longitudinal direction of the footing by using this UDL value. So this is the free body diagram of the footing, where you can see the foundation column location, column load acting in the middle, column factored load is acting at the middle, and the total UDL is acting in the upward direction. It is 537, and now you can use any method by which you can draw the shear force and bending moment diagram. You can use the force method, the area method, or any other suitable method. The point is that you at this level you have already studied about this force diagram, shear and bending, and you need to determine all the locations of the zero shear, point of zero shear, point of the maximum negative moment, point of the maximum positive moment, the location of the shear and the moment at the face of the column, location of the shear and the moment at the center of the column, the values and the magnitude, because we have to pick the critical values from this diagram. If you are just computing the few values at the known points, you will not get the criticals. You know that where the moment is maximum, where the shear is zero. And the where the shear is maximum at the supports, at the face of the support, where the shear is critical at a distance d from the face of the support. One-way shear. This is a one-way shear diagram. The shear force is basically telling us about the one-way shear because we have plotted this shear force diagram in one direction. We are not taking it as a punching. So this shear force diagram is first computed it simply from the force method. From the left hand, this here in the column load is taken as the point load in this problem. I will provide you one other problem solution where the column load is acting as a UDL. It depends upon the sizes of the column. So the column load is first taken. First the UDL is taken from the left hand column to the center of the column. So upward force 80 kilonewton. Then the downward load of 1352. It make it as a 1271 kilonewton. Then the UDL from the center of the column to the center of the next column. So that make it as a plus shear force of 14 and 14 kilonewton. Then again the downward load of 2032 and then again the upward UDL that make it finally 0. Your shear must be starting with the 0 and ending with the 0. Then from the shear force diagram you can compute the moment, or you can use any other method also, force method. Like the equation method I like, you can follow the equation method. I can provide you the equations of the all portion. You can divide your longitudinal footing diagram into the portion A, B, C, D, E and write down the equation, and from the equation you can draw all these values. Let's say you want to determine the zero shear, you put it the value of the shear equation equal to 0 and you can determine this x value. But here the x value where the shear is 0 is determined by using the similar triangle diagram. This shear is computed by the using the similar triangle diagram. You can determine the value of this zero shear 2.367 meter. Now you can take the area of this triangle, or you can put in the moment equation and you can determine this maximum negative moment 1498. So this was the most important point because we have to design the footing mostly for the maximum negative moment. So that comes out to be at the zero shear point. It is 1498 kilonewton meter. Now the shear is determined at the face of the column. As such, the face of the column was not any significant point, but you have to determine the moment at the face at the center also, because you know the values, you know the distances. So just put down the value of x or take the area of the diagram and you can determine the value. From this diagram, what we get? We get the shear at the support, shear at the face of the column. This is 1036. Shear movement, maximum negative moment at the center of the column. So maximum moment, negative moment comes out between the column, it is 1498. Maximum positive moment comes out the right hand side column, not the left hand side column, but the right hand side column gives us the positive moment because there is a larger overhang for the right handed column. And the positive moment at the center is 363 kilonewton meter. The positive moment at the face of the column is 237 kilonewton. So this is the most important part of this footing because you have to properly draw the shear and bending. If this step is wrong, whatever the procedure you like, you can go with that. But if this step is wrong, your next design will be wrong because you have to pick the values for the design from here. So your analysis for the problem must be right. And this start with the concept of the engineering mechanics and the mechanics of materials. So then the steps are just the design steps, and those steps are not always difficult because you have the known expressions, you have the known parameters. This formula for the thickness of the footing is a rough empirical formula that we use in the isolated footing also. So for the exterior column and interior column, the thickness is computed. Then come the depth of the one-way shear. So one-way shear, now we will pick the critical shear from the diagram. That was this one. And we apply the one-way shear check 0.75 to 1 over 6 FC prime BD. And normally the one-way shear check should be about 20% larger than the critical shear value. So shear is satisfied, but not satisfied actually. This was lesser. So we compute the value of the shear from this. So it is a one-way shear capacity is further reduced. 0.8 is basically this factor. We want to compute the D value. So D will be more when I further reduce the shear capacity. So from the one-way shear equation, I determine the D value. So D is computed from the one-way shear equation by equating it with the 5EC equal to VU, and the D value is taken. That comes out to be 773 millimeter. From that you can determine the H value. Because the cover plus the half die of the bar. Now the punching shear is computed, and how to get the punching shear in the combined footing. Actually, we don't know the tributary area for each column. Like in the flat plate and in the isolated footing it was known, but in the punching shear combined footing the tributary area for each column is not known. That's why the punching shear is taken from the factored column load. The total factored, the punching shear acting at each column is the factored column load minus the bearing pressure into the C plus D, the column punching perimeter area, C plus D square. C1 plus D into C2 plus D. So it is basically the tributary area was unknown. So we take the column load. Column load at the exterior column is there. Column load at interior column is also computed. Now the factored bearing pressure is also known. Pu1 plus Pu2 over area of the footing. Here we have to consider the total column load. No, even the reduced column load is fine. So the Qu is computed, and from the Qu we determine the punching shear. B naught is the punching perimeter, which is C1 plus D by 2 for exterior column. The reason for this D by 2 is that exterior column is only on one sided. Basically exterior column punching perimeter cannot be located on the edge because there is an edge of the footing. That's why you take it C1 plus D by 2 only on one sided, but on the other side there is C2 plus D, full width is considered. So punching perimeter is taken, and then from the punching perimeter you get the beta and all values, and 5EC is computed. 5EC are the three ACI criteria are standard, where first one is 0.75 into 0.33 FC prime B not D. Second one is this one into, and every parameter is multiplied with the B naught into D. And we see that which one is giving us the less value. The lesser will be selected, 1.107. So into B naught into D. B naught into D is taken for the exterior column, and VU, as I told you, that the punching shear in case of the combined footing will be the column load minus QU into C1 into the punching shear area within the punching shear perimeter. So this way we can get this. Here in the flat slab and isolated footing, we were using here also the tributary area into the factored load QU, but here we don't know the area, so we use the column load. So our check should be satisfied, and then we go for the interior column footing. The similar procedure is there, but here the D by 2 is not, but C1 plus D plus C2 plus D. So B naught is computed for the interior column, beta is computed. And then again the three checks are applied, and we see the 5EC. What we see is that the punching shear was not critical in this combined footing problem, rather the one-way shear was critical. Because combined footing take the larger load in the longitudinal direction, and when we plot the shear force diagram, it is very critical. Actually, we see that the shear in the one way was more critical compared with the punching shear. So we have our check with the computed from the one-way shear, the thickness that was computed from the one-way shear is satisfied. Now you pick the maximum moment, negative moment, MU, negative moment between the column and design the steel. So next one is the design for the flexure. Maximum negative moment is obtained between the two columns. So we pick the steel moment and design the steel. It should be larger than the minimum because it is a 300 megapascal steel. So yield strength of the steel. So therefore we will use at a 0.002 BH. And we decide the number of bars by area of the steel divided by the area of the one bar. And this is needed at the between the mids. This is needed between the two columns and in the overhang part, and where there is no requirement for the negative steel or beyond the development length plus D, we can curtail some of the bars. So let's say this bar is quite heavy reinforcement is obtained. So for the region where the minimum steel is needed or no top steel is needed, where the bending moment is converted, turned from the negative to the positive. But beyond the critical section, after attaining the development length, you can curtail 1/3 of the bars. So let's say 20 bars are there in the critical section, and in the other part, overhanging part of the footing, you can have the 7 or just 12 number of bars will be sufficient for the 12 bars in the overhanging parts, because we can curtail 1/3 of the steel in the other zone. Then is the positive movement. We pick the positive movement under the interior column, and the positive movement steel is even lesser than the minimum steel. As I told you that the positive movement is very small if the overhang is very small. So here the overhanging was not too lengthy, so positive movement is very small and minimum bars are needed. So it means that under the column we need the 18 number 19 bars, which is obtained from the minimum steel. So one thing is that even the minimum steel in the combined footing is not ordinary. What I have seen in the practical field, that the minimum reinforcement is even number 19 bars. And you see that in this footing, which is just 3 meter wide, we need the 18 number 19 bars. So this footing, why the thickness, the reason behind is the too much width and thickness of the footing. The width of the footing is 3 meter, it is more than 10 feet. And the thickness of the footing comes out to be 0.8 meter. So it's quite larger sizes. So these larger sizes are always demanding even the larger steel ratio. Then the development length expression will be the similar. You know that the bars cannot be curtailed before the LD plus D. So as per the criteria, the dowel bars are also needed, which are to be spliced with the column and extended into the footing. So you must see some detailing of the combined footing, and then the detailing guideline, these LD and these can be obtained. So I use the similar formula which I explained in the isolated and compute the development length for the different bars. So you know the number of the bars, and then you can apply the compute the development length. Why this development length is computed? You know that for curtailment and supplicement of the reinforcement, these are needed. Now the part of the exterior column is again there is a minimum steel, but you can provide the minimum steel under the exterior column longitudinal direction. So first we design the three steel, one steel in the, these all three steel were in the longitudinal direction. One is under the exterior column, one is between the column, one is under the interior column. Now the design of the steel under the transverse in the transverse direction. I have told you that in the transverse direction, you have to consider the bandwidth. So in the transverse direction, let's say this is the footing. This is the column of the footing. Now you make a strip here, strip like that. So this strip is equal to the C plus D. This strip is C plus D only in this zone, and similarly in the exterior column, under the exterior column, another strip is made which is C plus D by 2 because there is no D on the other side. So this strip in the exterior column is also C plus. So these strips basically, this strip and this strip, these need the heavy reinforcement in the transverse direction. So we have to get the column load under that, and these are giving us you can say that if you see these column in the cross section view of this part, it will be like that. So it means that in this zone, actually in this part of this this which is I have shown in the with the circle, I have shown with the this red circle. This zone basically in the bottom we need some extra steel in the transverse direction. It means that the steel will be placed in this way. Steel will be placed in bottom in this direction. Heavy steel is needed. Although the steel is needed in all throughout the width, but in this part, the heavy steel is needed in the bottom direction. So we need here the more reinforcement because of the larger load. Here we need the more steel under this. So how to design this transverse steel? How to design this transverse steel? So first we know the width of the strip is taken. Then the load on this transverse direction is the load over the simply the column load divided by the width of the footing. So that become the UDL, and then take it as isolated footing and simply compute the moment. How to get the moment? Moment is the load on this transverse strip which is equal to the column load divided by the width multiplied by the moment arm. What is the moment arm in the transverse direction? This moment arm is from the edge of the footing to the column face. So this moment arm is B by 2 minus C by 2. This will be B by 2 minus C by 2. So moment will be load into the UDL into B by 2 minus C by 2. It is a loading length, and half of that it will give you the bending moment. So this bending moment is computed. From the bending moment you can determine this reinforcement, and this is a bottom steel. So this steel is needed. Larger than the minimum steel, so you select the again the larger bars, 5 number 22. So this is a quite heavy steel, or anyway even the 19 bars, about 9 number 19 bars are needed. Similarly, you design this for the interior column width, you compute the interior column and then compute the bending moment, and the same steel is also needed under the interior column. In the other part of the footing, you will just go with the minimum steel, which is the other transverse part, which is other than the bandwidth. We will provide the minimum steel. You check the development length, that whether this minimum steel, the development length is obtained in the width of the footing, or you need certain hook. If the development length can be obtained from the critical section, then it's fine. Otherwise, you can turn the bar on the right side and make the 90-degree hook and make it, because the thickness of the footing is also large. So the development length can easily be obtained by making the hooks also. But it is even lesser than 895. So our projected length is larger than 1 meter. So it means that the transverse steel is fully developed. Now in the combined footing, if you overall see, there were many places where there is no steel is designed. What are the places where the steel is not designed? I can tell that bottom steel between the columns, this location, the steel is not designed. Top steel under the column, transverse steel at top between the columns. So some of the steels are not designed because there was no flexure there. As per the code requirements, we will provide the 0.001 BH steel there. We will compute the value of that steel reinforcement 0.001 BH, and that steel is provided throughout the footing where there was no steel. So one steel, this amount number 13 at 150, it comes out to be the steel which is needed for the throughout the width of the footing where there was no flexure, like the other than the strip part. Similarly, the hanger steel for the top steel. So finally, this is the sketch of the footing. There the main steel is shown, which is designed, and the other steel will also be provided, which is not designed. That will be the minimum steel, but here in this sketch, the main steel is shown for the combined footing. You can see that this 20 number 22 bar was the longitudinal direction, negative bending moment. 80 number 19 bar is the longitudinal direction, positive moment. 8 number 22 bar, transverse direction, bandwidth, interior column. 5 number 22 bar, transverse direction, bandwidth. And the remaining zone, which is the top steel in this part and other part, you can go with the minimum reinforcement. So you can show all the bars in the cross section, and for all the types of continuous footing, the idea, the overall, the concept remain the same. Whether there are one column or more than one column, or two columns or three columns or four columns, the movement between the two columns mid span is normally negative. Movement under the column is positive. And in the transverse direction, the bottom steel is heavy under the column. The reason is I have explained that there is a major bending occurs also in the transverse direction, but under the column. Between the columns, normally the transverse direction is not critical at the bottom, but longitudinal direction bending is very dominant between the column in the longitudinal direction. So you have seen that what was the steps involved. I can review the steps. First of all, you start with the computing the load, location of the computing the area allowable net bearing pressure, then service load, then location of the resultant, X bar value, then you can compute the length value, then the width required, area of the footing required, and you finalize the dimension of the footing. Then you draw the shear and the bending and find out the critical forces, decide the trial depth and apply the one-way shear jack. So that was not satisfied, so you compute the depth of the footing by the one-way shear criteria and check for the punching shear. The punching shear is computed by the column load minus the load acting within the punching perimeter, and from that you get the value of the punching shear, and that those checks were satisfied. Then you go ahead with the flexure design. So you start with the longer top steel which is between the column, then the bottom steel under the column, longer direction bottom steel. Then you compute the transverse steel under the column, interior column and exterior column. You compute the load and the moment arm. It was from the B by 2 minus C by 2 square. So then you can find out the steel in the transverse direction. Then you compute the development length, and in this way you complete the problem of the combined footing design. So do you have any question from this design problem of the combined footing? You can ask me. Yes. Any question from your side?
सर राफ्ट फाउंडेशन भी डिजाइन करेंगे या बस फाउंडेशन यहीं तक करनी है हमने से?
Yes, in the next lecture we will see.